We'll discuss in detail about the mathematical models of control systems. We'll start with open loop control system. So this video you may find it a little bit laggy, so you may watch at 2 times of speed if it is required. So this is intended for those who wanted to understand in deep of control systems rather than just going it. Everywhere the control system plays a very prominent role, starting from economy, biology, sociology, medicine, etc. Everywhere, the control systems is being widely used in industry. For example, if you wanted to control some sort of temperature in your home also, you are using some control system. So there are two kinds of control systems. One is open loop control system, other one is closed loop control system. So in the open loop control system, generally what we do is here let us take a system. Generally it is called plant, a system or a plant. So this plant word has come from the earlier days it was something about to plant. So for this plant, the input that we are giving, I am considering that input as R of t. It is processing to the plant or a open loop system, and the output that we are getting is C of t. For instance, let us take one example that suppose with your remote, so I'm assuming you are in the room and you wanted to set a temperature. With a remote to your air conditioning system, you set a temperature to be 30 degrees. Okay. Now, whether you are getting 30 degrees or not, that will not monitored by your plant or controlled by your system. For example, if you take one more sensor and you can see how much amount of temperature it is, based on that requirement, if you change your plant parameters, then this type of system is called closed loop control systems. That much simple it is. So basically the main difference between open loop and the closed loop control system is, in open loop control system there is no feedback, in the closed loop control system there is certain feedback. So in general, how the closed loop system will be represented, you can see here. Suppose you have a system, or I can say it is a plant. You have a plant something like this. This plant, you are getting some sort of a output. For now I am assuming temperature as the output. Now here what are we trying to give is, you wanted to give your input as some temperature. So this is a reference input. This is also called as a R of t. Okay. So this input, whenever you are giving, it is not directly going to the plant. In between something is sitting, that is what actually doing entire job, that is called controller. So this controller is sitting here. The information from the reference, whatever you are giving, that information is going to the controller, it is going to the plant, and you are getting the output. Once you get the output, the output may be in the form of a voltage, output may be in the form of a current, whatever it is. So that information, whatever the information that is there, that you have to sense first. That sensing of that information is done by your sensor, and it is called the feedback. The information that you are sensing, you are trying to compare. Suppose here you are getting output in terms of temperature. That temperature may be in the form of a voltage or something like that. So that information that you are carrying out, converted into required form, and then it is passing through this. So whatever the signal that you are giving as input, that signal is compared with the output, and then required signal will be processed through the controller. The controller will give corresponding signal to the plant. So this particular portion is called the error detection. this particular portion is called the error detection. So what actually it is doing? It is detecting the error. What error? Whatever the input that you are giving, say for example 30 degrees centigrade that you are giving, here it say you are getting 35 degrees centigrade. So the difference between your commanded or reference value and your actual output value will be compared in this particular scenario, and then it is given a command signal to the controller to act. So that is why it is called the error detection circuit. This type of control system is called the closed loop control system. Okay, so there are so many advantages and disadvantages between the closed loop control system and the open loop control system. As you have seen that the closed loop control systems are trying to make the system accurate even in the presence of some sort of noise or non-linearity, and the closed loop systems are less affected by the noise, whereas the open loop systems are vice versa. Open loop systems are inaccurate and unreliable, but those are simple to construct. That is the only basic difference between the open loop control system and the closed loop control system. So you can take any sort of example, the traffic, the temperature, and the speed, the position, so many things are there. So I don't need to tell you in detail about this. Those are all the very simple way you can try to understand. Now our main agenda here is how do we represent these all sort of control systems, because the systems are mechanical in the form, the systems are electrical in the form, the systems are various in the forms are there. Our main intention is we wanted to bring the system from all different kind of forms to a particular form. That is what we call as a mathematical form. So then that particular mathematical form we will try to study, and then we will utilize this in terms of control systems. So in starting of that, so let us take one particular item that is called mass. So this is the mass m. So for this particular mass, I am assuming this is an ideal mass. So this is having certain reference value. So this I am putting as a reference. This is having certain reference value. For this mass, I am giving certain amount of force, that is applied force F. So when you apply certain amount of force on the mass, what will happen? The system will try to displace. So the displacement I am representing it as x. So and when you try to apply the force onto the system, what will happen? There is some certain amount of reverse force, that is called opposing force, due to the mass that will happen. So that force should be overcome, then only the mass will displace. So the total force that you are applying is equal to the opposing force, then only the system will respond. F is equal to m into a. So the mass into acceleration. So acceleration can be written as d square x by dt square. So for now, whatever the system that you are able to see in the form of a mass, that F can be written as m into d square x by dt square. This is as per the Newton's second law of motion. It is the same thing. Similarly, another important element that is also called that ideal frictional element, that is also called as a dashport, I can consider. So the symbol of dashport is something looks like this. This is tied to a particular reference. This is tied to a particular reference, and on this dashport also you can apply certain amount of force. You can apply certain amount of force onto this particular dashport, and when it is also you apply force, it is also can display certain amount of distance x. So this dashport is something like a frictional component, a friction component, which is having the negligible mass and the elasticity. So the force applied on the dashport is directly proportional to the opposing force due to its friction. So the force apply on the dashport, say let me assume that the frictional force is Fb, that is directly proportional to dx by dt. So the total the frictional force, or F, I can say F is equal to Fb into, so the dashport constant I am just taking as b into dx by dt. This is another important term. So one is with the ideal mass element where you have seen here, another one is with the frictional dashport element. Okay, now what you can see, for suppose when this dashport has not connected to anywhere, and it is displacement at the both ends of the site. Say for example here this is the case. When the dashport, I am just considering the dashport here, instead of fixing to certain reference, it is just left it. So when you apply certain amount of force F here, so it may displace by a distance x, or I can say x1, and here also it is not at all connected to anything, it may also displace by a distance x2. At the time the frictional force, or the total force that you are trying to apply, Fb is directly proportional to b into, Fe is directly proportional to, the frictionality constant will come there, Fb directly proportional to d by dt of x1 minus x2. So if I remove the proportionality constant, the Fb is equal to b into d by dt of x1 minus x2. Okay, so we have seen the mass and the dashport. So now let us consider an idealistic elastic element. So the elastic element is represented in the form of a spring if this is connected to a fixed reference. Okay, so the spring constant, say k, and when you are applying certain amount of force onto this, it is displaced by a distance x. Okay, so this is a reference. The amount of the force that you are applying is equal to the opposing force due to the elasticity. So that elasticity force is k. So let me assume that Fk is directly proportional to the x. So if I remove the proportionality constant, so this Fk will become Fk is equal to F is equal to k, proportionality constant, into x. Suppose if the same system is displaced at the both ends, say here this is spring and it is not tied to any sort of reference, you are applying certain amount of force onto the spring, it is displaced by a distance x1 and it is also displaced by distance x2. The total force, that is Fk, is directly proportional to the difference between the distance, that is x1 minus x2. So considering the spring constant k, Fk is equal to F is equal to k into x1 minus x2. This is how you can design the system very easily. I mean, like, so since you have seen the mass, the dashport and the spring, these are all very easy. In a summary nutshell, I can just explain you that when you take the mass into action, so F is equal to m into, m is the mass, d square x by dt square. F is equal to b into dx by dt. F is equal to k into x. If these are not displaced, then the formula will become m into d square by dt square into x2 minus x1 if they are displaced by, I mean, if it is not tied to one reference and it is leave it, then b into d by dt of x2 minus x1. You can also write x1 minus x2. There is no problem. It depends upon which is the big element. There is no this thing here. A k into x2 minus x1. So these are the three things that you are need to put into focus into your mind when you are trying to solve any sort of systems. So let us take one simple example and then try to solve how are we trying to do it. Okay. So one example I'm just taking. So let me take with a different color and then see what is the color like. So I'll take a white color. So the question I'm just writing into what color. So here, so what I'm taking is, I'm taking some sort of a spring that is tied to mass, okay, that is tied to mass m1, and this is connected to one particular dashport, and then it is also connected to one sort of a spring, and it is connected to another mass m2, and here you are trying to apply certain amount of force f of t. So these are all in between. I am assuming there is some sort of a reference here. For this reference there exists a frictional coefficient, say b1 here, and there exists a another frictional coefficient, say b2, and this spring also, let me assume that it is also connected to some sort of a reference, and the constants are k1, okay, and when the mass is given here, it is displaced by a distance, say x1, and if the mass another, depending upon the force, this is also displaced by distance x2, and the dashport constant is say b, and the spring constant, say k. Now this is the system. While doing the system, so the Laplace transform is the one where you can see everything in a very easy fashion. So you need to understand that Laplace of x of t, so Laplace of x of t can be written as x of s. So generally if the flower bracket also can be made here. So Laplace of d by dt of x of t can be written as s into x of s. Laplace of d square by dt square into x of t can be written as s square x of s. So where all I am considering that the initial conditions are 0, otherwise that minus term will going into add, and then the initial term will come into picture. Suppose if you get this kind of problem, I mean like to solve, it is how do we solve it, that we need to check it out. So let me change the color of the pen so that it will be easy. Okay, so now the first things first. So we need to solve this. Simply, very, very simple that we have to solve with this. First, let us take a body mass m1. On m1, what are the forces that are acting in and out, that you have to consider. Okay, suppose this is the mass m1, this is the mass m1, and what are these forces that are acting. So here if you observe, on the mass, the distance that is taken, I mean on the other direction x1, so the forces that are acting is the k, the forces that are acting is the b, the force acting as the k, the force acting as the b. So like this there are so many forces that are acting. So as per the Newton's law, sum of all forces are equal to 0. So what I am writing is the force that is due to the spring Fk1, the force that is due to the mass, so I am writing as m1, Fm1, the force that is due to the dashport, that is Fb1, the force that is actually displaced in between the b, okay, is Fb, the force that is there due to k, that is equal to 0. One important thing that you need to observe, this particular k and b are exist in between m1 and m2, rest all are okay. So as per our initial just now whatever the mathematics that we have seen, based on that that fk1 can be written as, so k1 is, this is 1, okay. Fk1 is just directly k1 into x1, and m1 is m1 into d square x1 by dt square, plus fb1, so b1 is just associated with only this thing, so b1 into dx by dt, plus fb. Now the b is associated in between x1 and x2, so that one what I am writing as b into d by dt of, here you observe carefully which is bigger, so x1 minus x, so from here we have to take x1 minus x plus k into x1 minus x is equal to 0. So this is in the form of a full differential equation. Now we can solve this differential equation by applying the Laplace transforms. So how do we apply the Laplace transform? Here k1 x1 of s plus m1 s square x1 of s plus b1 x1 of s plus b s into x1 of s minus x of s plus k into x1 of s minus x of s is equal to 0. Okay, that is how we have to make it. So slowly we'll come back and then see. So here we have come. Now you can see here, now we need to separate the x term and the x1 term and x term. So if you take x1 as a common, x1 of s as a common if you take, so this will become m1 s square plus b1 plus b into s, because I am just coming from the top to bottom s power, there is nothing deal here, that is plus k1 plus k1 plus k is equal to x of s into bs plus k. Now our main intention is to find out what is x1 of s, that's all, right. x1 of s is equal to x of s into bs plus k divided by m1 s square plus b1 plus b into s plus k1 plus k. That's all. That is for the x1. So whatever you have solved is for x1. Now let us solve for x2. Okay. Similarly, so let me take this particular portion of this this thing. So I'll just copy this. So I'll copy it, I'll paste it here, and then I'll solve for the other thing. That is, for the M2, what are the things that we need to solve? So similarly, whatever we have discussed earlier there, for the M2 also we will discuss the same thing. What are the forces that are acting on the M2? So the forces that are acting on the M2 is the mass itself, F m2, plus the b2, F b2, plus and Fb, so that is b, that is acting in the both side, plus Fk. Fk is equal to this particular force F of t, that is more important. Now again same, let us apply the same formula again and then we will try to solve here. So here Fm2 can be written as m2 d square x by dt square plus Fb2 b2 dx by dt plus b d by dt of, here the two differences. Now it is now x minus x1. Earlier it was x1 minus x. Now this x minus x1 plus k into x minus x1 is equal to f of t. Okay. So now you can see, so applying the Laplace transform to it, this will become m2 s square x of s plus b2 s into x of s into x of s plus b s into x of s minus x1 of s plus k into x of s minus x1 of s is equal to f of s. Okay, now let us take the this x part and x1 part apart. Now what you will get is, when you apply this symbol this, so taking x of s into common, x of s if you take common, that is m2 s square plus b2 plus b into s plus k minus x1 of s if you take common, x1 of s, that will become bs plus k is equal to f of s. So from, our main intention was, to find out the transfer function. Transfer function means Laplace of output by Laplace of input. So here the output you can see here is f of s by x of s or x of s by f of s. So you can take whatever the form that you wanted to have. If you want to find out x of s by f of s for the given output, so for the f of t you are giving as input. In this scenario, if you observe here, you are giving f of t as a input here, and the total x is your total x is what is displacement that is happening. So this x2 I am writing as x, okay, so that it will not be confused for anyone. So now for the given input, what is the output that you are giving? So our intention was here to find out x of s by f of s. So to find out that particular thing, we have got whatever the equation are suppose. So we got what is x1 from our earlier system, x1 we got. So let us substitute that x1 here. So x of s into m2 s square plus b2 plus b into s plus k minus x of s is equal, x1 of s is equal to x of s into bs plus k into bs plus k, that will become bs plus k whole square divided by m1 s square plus b1 plus b into s plus k1 plus k is equal to f of s. That's all. So now we can take it out and make a beautiful transfer function, multiplying here and there. So what you will get, our intention was x of es by f of es is equal to, so this one will be cross multiplied with this and then it will go other side. So what we'll get finally m1 s square plus b1 plus b into s plus k1 plus k divided by m1 s square plus b1 plus b into s plus k1 plus k into this entire multiplication with this thing, that is what m2 s square plus b2 plus b into s plus k minus bs plus k whole square. That is how you can easily find out the transfer function for this particular scenario. So what if when you are applying for some sort of a competitive examinations and all those things, so we will not you may not get that much amount of time to solve it, right? So how do you do that? Simply you can solve by taking the differential equation to this particular thing as m1 d square x1 by dt square plus b1 dx1 dt plus b into d by dt of x1 minus x plus k1 x1 and plus k1 into x1 minus x plus k1 x1 k into x1 minus x is equal to 0. So something like that you have to make it so fast, and then simply we can able to do that. So let us so considering this one particular problem, let us solve one more problem to have a clarity in understanding, and then clear cut in whatever we will do, let us do it very clearly. So let us take one more simple example. So let me take so this is not visible, so I'll take another color. So yeah, sorry, pen settings, I'll take a kind of white color. So let me take, there is something reference here. For this reference, okay, this is a reference. For this particular reference, there is a spring and there is a dashport. These two are connected to a mass. That mass we are writing as m1, and this is also connected to another spring, and it is tied to another mass. This mass I am writing it as m2. So it is displaced with a distance of y2, let me say, and this spring constant is k2, and here the displacement is happening with a displacement of y1, and the total input force that you are giving here is f of t. This constant I am considering as k1, this constant I am considering as b. So it's also very simple as what we have discussed earlier. So same thing, first of all let us consider the masses, the free body diagram for the mass m1. So I'm just taking one left half here and one right half here, so that I will just try to solve in this particular figure itself. So here, as per the theory, the forces that are acting on the particular mass m, I am writing as F m1 plus Fb plus Fk1 plus Fk2, that is equal to f of t. So m1 is only the mass m1 into d square, it is y1 right here, d square y1 by dt square plus b into d y1 by dt plus k1, that is k1 y1, that is k2 is now sandwiched between m1 and m2, so it is having force, that is k2 into y1 minus y2 is equal to f of t. That is very simple. So our intention was output y2 by ft. Okay, so now let us bring the into the Laplace transform. M1 s square y1 of s plus bs y1 of s plus k1 y1 of s plus k2, so I'm just multiplying here, okay, y1 of s minus y2 of s is equal to f of s. So if I rearrange, taking the y1 into common, I'll write as y1 of s is multiplied with m1 s square plus bs plus k1 plus k2, that multiply minus y2 of s into k2 is equal to f of s. So that is how you have to write the f of s value particularly. So likewise, we will take the value of f of s here. So similarly, let us draw the free mass diagram for the mass m2. So similarly, let us draw the free body diagram for the mass m2. So for this particular mass m2, so here that's also simple. So what are the forces that are acting on the k2, which is sandwiched between m1 and m2 and y2? That's all right. So that is here the force that is acting here, F m2 plus F k2 is equal to 0. That is m2 into d square y2 by dt square plus k2 into y2 minus y1 is equal to 0. So applying the Laplace transform here, that is m2 s square y2 of s plus k2 y2 of s minus y1 of s is equal to 0. So now by substituting this value, what y1 will get here is y1 of s is equal to y2 of s into m2 s square plus k2 by k2. Now you can substitute y1 from the earlier this thing. From here you can substitute the y1 here. So by substituting the y1, so here y1 is equal to, so by substituting the whatever the value of y1 that we have solved, y1 is equal to y2 into all those things. So now see this particular y1 value will substitute this or this one to this, whatever you want to do it. So here you can write y1 I'm substituting here, that is y2 of s into m2 s square plus k2 by k2 into m1 s square plus bs plus k1 plus k2 minus y2 of s into k2 is equal to f of s. So if you rearrange and shuffling, so the output is y2 of s by the input f of s is equal to k2 divided by m1 s square plus bs plus k1 plus k2 into m2 s square plus k2 minus k2 square. That's all. So in entire the scenario it is very easy to solve. Okay, likewise whatever the equation that you can do, that equation can be written and then find out its mass and then find out its free body diagram and make around it. So these are all called translational mechanical systems. So whatever we have discussed till now is mathematical modeling of a translational mechanical systems.